Okay, here we have a galvanometer, which essentially consists of a coil of wire inside a magnetic field. If I was to crank this generator, attach the leads to the galvanometer terminals, and crank it, there's a very good chance that I wouldn't be able to crank it so gently that it didn't destroy the galvanometer, because the galvanometer is pretty sensitive. I'm not going to test that. It doesn't matter. I know that it'll work because I know how this is designed, and I know how the thing that we observed with the aluminum strip across the magnet translates to the way a coil of wire, a loop of wire, behaves inside a magnetic field. It's very straightforward. We can develop that very easily from what we have observed about the aluminum strip carrying the current of the generator in the presence of a magnet. Now, that's not what I want to demonstrate right now. Simply I want to make the point that it's very easy to verify that the type of electric current that we get from a lot of static electricity, Benjamin Franklin and his Leyden jars back in the late 1700s, is the same as the flow of current that we get from this generator, and that's going to be illustrated by what happens when we change the magnetic field through these loops. Okay, so without further ado, so I'm going to very slowly move this magnet into the vicinity of this first loop, and then the magnetic field of the magnet is penetrating the loop in this direction, at least right in front of the loop. Now, the field of the loop actually, or the field of the magnet actually kind of loops around this way, and we'll illustrate that later once we talk about how dipoles act and so forth. Right now, you can just think of this magnet as creating a magnetic flux through this loop. The component of the magnetic field that gets to this loop and goes through it integrated over the interior of the loop, that would be the magnetic flux, is right now constant. But if I rotate the magnet, now the magnetic field is only a small part of it is penetrating the loop. Most of it's going off this way and back this way. Okay, so if I suddenly rotate, see what happens. You see there was a current. Now, hopefully you saw the needle of the galvanometer deflect, but let's just do it the other way. It deflects in that direction. Okay, if I move it slowly enough, you won't see much deflection, but a little bit. The faster I move it, the greater the deflection. Now, there's some latency in the response of the galvanometer, so if I move it too fast, you won't really get the full picture. There's a limit to how fast that needle can move. There's some elastic properties and so forth within the mechanism that prevent it from responding instantaneously. We get around some of that with good electronic instrumentation, but we're not going to bother with that right now. We just want to see that when we change the magnetic field in the loop, we have a current. And if we change the magnetic field more quickly or more slowly, we get more or less current. If I put the magnet within these two loops, we actually get a greater response. you can compare that just visually. Because the way these two loops are oriented, the change of the magnetic flux in one is going to reinforce the effects of the change in magnetic flux through the other. I can do other things. I can change the magnetic field just by dropping the magnet, or I can toss the magnet through the loops, depending on how the orientation is. And if I had really good fingers, I could spin the magnet. Okay? I can spin the magnet, and looks like somehow I managed to, in catching the magnet, I disconnected one of the leads. Okay, if I spin the magnet, we can see how we get an alternating current. Okay, well, all that needs to be developed with some pictures on the board and some mathematical symbols in order to really get a handle on how it behaves, but it's fairly straightforward once you see, well, assuming you know multivariable calculus, it's pretty straightforward. And once you see the symbols and everything, this should help you make sense of what you're looking at.